The following question reads that the table gives some data for elements in the third period and some of their compounds. So the third period elements are given from sodium to sulfur and the type of bonding, etc. There's one row for the type of bonding, one for the formula of the oxide, and the third one is for the formula of the chloride. And the first thing is we need to complete the table to show the bonding in the elements and the formula of the oxides and chlorides. So the bonding in the first three elements, sodium, magnesium, and aluminium, they're all metals, and the bonding is metallic. And here is the structure of metallic bonds, where you're going to have all these metals, sodium, magnesium, and aluminium. They're going to lose electrons. They're going to form positive ions. So there's going to be a lattice of positive metal ions in a sea of free-moving electrons. So there would be delocalized electrons that would be freely moving around, and metallic bonding is going to be strong because positive ions and delocalized electrons, they are going to attract each other, positive and negative. So these delocalized electrons are going to attract each other very strongly, the positive ions and the delocalized electrons. Let's discuss silicon now. Silicon is a macromolecular structure. It's a giant covalent structure, and the bonding in silicon is going to be one silicon bonded to four other silicon atoms as shown in the diagram, and those silicon atoms are then again bonded to four other silicon atoms, and the bonding continues. So it's a giant covalent structure with lots of bonds. It's going to be a very strong structure and high melting and boiling points because lots of bonds are going to be broken, need to be broken to melt it or to break it. In the next row, we need to construct the formula of the oxide. So the first one is sodium oxide. Sodium is +1 and oxygen is -2. So it's going to be Na2Os. Mg, magnesium oxide, is going to be Mg is +2, O is -2, so it's going to be MgO. Aluminium oxide would be Al is +3, O is -2, so it's going to be Al2O3, whereas silicon oxide is SiO2. It's a giant covalent structure as well. So these are the formulas of the oxides, and then we also need to construct the formula of the chlorides. So I'm going to use the same oxidation state, which is that Na is +1, Mg is +2, Al is +3, Si is +4, and P is +5. So let's start constructing the formula of the chlorides. For Al, it's going to be AlCl3, which is actually a covalent molecule. Instead of being ionic, it's a covalent molecule. So remember this exception. The other one for silicon, it's going to be SiCl4. Silicon has an oxidation state of +4. Phosphorus can have an oxidation state of +3 as well as +5. So I can come up with two chlorides. One would be PCl3, and it can also be PCl5. Phosphorus can expand its octet, and it can have multiple bonds. It can make 3 bonds. It can also make 5 bonds. So there could be PCl3. It could also be PCl5. Now let's move to the next part of the question, which is that you're given HCl2 is formed in the following reaction. And you're given an equation, and the enthalpy change for that reaction is also given. And we need to complete the dot and cross diagram to show the bonding in a molecule of SCl2 to show outer electrons only. Now the first thing is S would be in the middle. It has 6 electrons. So that means that out of the 6, only it needs 2 electrons. So it's going to be sharing 2 electrons. And Cl is in group, it's in group 7. So it has, I'm going to draw its electrons. I'm going to use the symbol crosses. So it's in group 7. It shares only 1 electron. It needs 1 electron. It shares 1 electron. The other Cl is also in group 7. So these are the 6th electron. The 7th electron is going to be shared. So remember, in covalent molecules, if sulfur is in group 6, it needs 2 electrons. It shares 2 electrons. So 6 electrons, and it's sharing 2 electrons. 4 electrons are left behind. Chlorine is in group 7. It shares 1 electron. 6 electrons are left behind. This one is also sharing 1 electron, so 6 electrons are left behind. Let's now move to the next part of the question, which is that complete and fully label the reaction pathway diagram for the reaction between H2Cl2 and Cl2. Include labels for, so we need to label the activation energy and the enthalpy change of the forward reaction, delta H. So these need to be labeled, and we have to draw a reaction pathway diagram. The first thing we need to go back and have a look at the reaction. Remember, it's an exothermic reaction. Delta H is given as minus 40.6 kilojoules per mole. So it's an exothermic reaction. What happens in exothermic reactions? The energy is lost. So these are your reactants. So here you have your reactants. So if energy is lost, the product would have lesser energy. The vertical axis, the products are going to be lower down. They're going to lose energy. It's an overall exothermic reaction. The forward reaction is an exothermic reaction. So as you can see, the products have lower energy. This is the overall energy change. This is going to be your delta H, which was given as minus 40.6 kilojoules per mole. So this is your delta H. Remember, delta H is the overall difference between the reactants and products. So you're going to start at reactants and you're going to end at products. The other arrow that we need to draw is the activation energy, or the energy that is initially needed to start the reaction. So it's going to go start from the reactants again, and it's going to go all the way up. Remember, reactions need energy at the beginning because they need to break the old bonds first, and only then new bonds are formed and energy is released. Let's go back and look at our equation and see what the products were. SCl2 were the products that were formed. So go back and write your products as well. It's going to be 2 SCl2 molecules that are being produced. So this is your fully labeled energy pathway diagram that we have drawn. In part C of the question, on the axis, sketch the trend in melting points of the elements sodium to sulfur. And this you need to remember. So this over here is the overall sketch. Sodium, Mg and Al, the first three are metallic, but Mg and Al have stronger metallic bonds. Sodium has a relatively weaker metallic bond, so it has a melting point that is less than 100. Silicon is a giant covalent structure, whereas phosphorus and sulfur are simple molecules, and they are going to have lower melting points. Now, we need to explain this sketch in detail. We have to give three statements to explain our sketch. So first thing is, I'm going to first comment on the melting point trends of Na, Mg, and Al. The first explanation that I'm going to give is for Na, Mg, and Al. The reason is this, that Na, Mg, and Al are all metallic. But metallic bonds are going to become stronger as you move from Na to Mg to Al. And the reason for the stronger metallic bonds is because you're going to have more delocalized electrons. I've drawn two sketches where I'm going to show, and I'm going to compare Na and Mg. You can see that Na is in group 1, so its ions are going to have a charge of +1. It's only going to lose 1 electron. So the delocalized electrons and the positive ions in the metallic lattice, the attraction is going to be weaker compared to Mg, where Mg loses more electrons. Mg is in group 2. It loses 2 electrons. Each Mg atom loses 2 electrons. So there are going to be more delocalized electrons. More electrons that will be randomly moving around, freely moving around, and the charge on the Mg ion is going to be +2. So the attraction between the +2 charge and the higher number of delocalized electrons is going to be greater. So the metallic lattice is going to become more stronger because the delocalized electrons are more. The ionic radii also decreases. Mg +2 ion is going to be smaller, so they're going to be more tightly packed together. If they are closer together, then they're going to attract each other more strongly. And the third reason is that the ionic charge is also increasing. So the charge on the ion in the metallic lattice also increases. So you can follow the trend, and you can then think about aluminium. Aluminium will have a charge of +3 in its ionic lattice, in its metallic lattice, and it's going to lose, each aluminium atom is going to lose 3 electrons. If it loses 3 electrons, the amount of delocalized electrons is going to be even greater, and aluminium is going to have even higher melting and boiling points. So this is the first trend that I've explained, that from Na to Mg to Al, the metallic bonds are going to become stronger. Now the next element that I'm going to discuss is going to be silicon, because silicon has a very high melting point. So we need to, because we had to comment on the sketch, we had to make 3 statements to explain our sketch. So this should be part of it. Silicon has a very high melting point. So we need to give a reason for why silicon has a higher melting point. As I've already stated previously, silicon has a giant covalent structure where you have silicon atoms bonded to 4 other silicon atoms, silicon atom again bonded to 4 other silicon atom, and the network of covalent bonds continues. So it's a giant 3-dimensional covalent structure, and it's going to be very strong because each atom is covalently bonded. It's making very strong bonds with the other atoms. So it's a very, very strong structure. So it's a giant covalent structure. That would be the answer, or that would explain the high melting and boiling point, because a lot of energy would be needed to break this structure. Lastly, what I'm going to comment on is I'm going to comment on phosphorus and sulfur. They have low melting and boiling points, and the reason is because they're simple molecules. So I've written this down that phosphorus and sulfur have simple molecular structures with weak van der Waals forces. So you're going to have a molecule of phosphorus, and that would be attracting. So you're going to have two molecules of phosphorus. Phosphorus, remember, is P4 in molecular form. So there would be two P4 molecules. Let's draw another one, and those molecules, they would not be attracting each other very strongly. They would be very weak. There would be no bonds in between, but just weak intermolecular forces. And the intermolecular force that's present is van der Waals forces. So they're going to have they're going to boil or melt very easily. So they have weak van der Waals forces between them, and the reason why sulfur has a higher melting point is because sulfur has more van der Waals forces. It is a bigger molecule. The molecule of sulfur is S8. It has more atoms in it. The molecule of phosphorus is P4. It has lesser atoms in it. So van der Waals forces, or the temporary dipole-induced dipole interaction, depends on the size of the molecule. If the molecule size is bigger, it's going to have more van der Waals forces. So the melting point of sulfur is greater. So they are simple molecules, both phosphorus and sulfur. They're simple molecules with weak attractive forces between them, but sulfur has a bigger molecule and it has more van der Waals forces. Now, in the next part D of the question, you're now being asked to write an equation for the reaction of P4O10 with water. So you have P4O10. The first thing you should notice is that P over here, the oxidation state is +5. So P4O10, if you react it with water, it's going to form an acid, and it's going to specifically form phosphoric acid. The reason you should choose phosphoric acid instead of phosphorus acid is because phosphorus has an oxidation state of +5. So in the acid that is formed, the oxidation state should still remain +5. And you just need to balance the equation now. So there would be 4 phosphoric acid molecules because there are 4 P's over here. There should be 4 phosphoruses over here as well. And that would give you 12 hydrogens. So I need to multiply this by 6. And that is how the equation would be balanced. Let's move to part E now. SO2 can be released into the atmosphere when fossil fuels containing sulfur are burnt. State and explain one environmental consequence of the release of SO2 into the atmosphere. Now, sulfur dioxide produces acid rain, and you should write in detail. It's again a 2-mark question, but you should write in detail how acid rain is formed. So the first thing is I've written down equations for the formation of acid rain. What happens is sulfur dioxide gets oxidized in the atmosphere into SO3. Usually it's NO2 that oxidizes it, and ends up forming NO. So SO3 then reacts with water in the rain and ends up forming sulfuric acid. So this is what you call acid rain. So a few molecules of rain are going to react with SO3 in the atmosphere to form a few molecules of sulfuric acid. Now, one environmental consequence of this is that the soils and water bodies, they would become acidic, and fishes and plants, etc., they need a very specific pH, usually close to neutral, in which they grow very well. So if the pH of the soil or water bodies changes, then it would be difficult for animal life or plant life to actually survive, and they get affected. Part F of the question reads now that the elements in the third period show a general increase in the first ionization energy of from left to right. And we need to identify 2 pairs of successive elements in the third period that do not agree with the statement. For each pair, explain why the change in ionization energy does not agree with this statement. So we need to explain that. So the first thing is we're talking about the third period, and across the third period, we're moving across the third period. So very quickly, let's first go through the ionization energy, the first ionization energy trend across the period. As you move across the period, in period 3 from sodium, magnesium, aluminium, so you can see that there is a general increase in ionization energy as you move across the period. And what's the reason for that? So there are 3 main factors which determine why the ionization energies are increasing across the period. And the first one is that the nuclear charge, the number of protons, keeps on increasing. So there's more attraction for electrons. Sodium has 11 protons, Mg has 12 protons, aluminium has 13 protons, and protons keep on increasing. So you have more protons as you move across the period. So there is going to be more attraction for electrons. The other factor is that the shielding is constant, which means all of the elements have exactly the same number of shells. So the electron is going to be, the shielding effect is going to be constant. And the atomic radius keeps on decreasing as well. The electron becomes closer to the nucleus because of the stronger attraction. So the closer it is, the more attraction there's going to be. So it becomes more difficult to remove electrons, hence the ionization energies keep on increasing. Now the question basically deals with these 2 pairs that do not follow the trend. So the entire question about two pairs that are not following the trend. For example, aluminium, there's going to be a dip in ionization energy across the period at aluminium, and there's going to be a dip in ionization energy across the period at sulfur as well. So we need to explain these dips now. So let's go back to the question. And here's the question. I've opened the question again. Let's look at it. We need to identify two pairs of successive elements in the third period that do not agree with the statement. So we've identified the first pair, and that is magnesium and aluminium. And we need to explain why aluminium's ionization energy is lesser compared to magnesium's ionization energy. So I've written down the electronic configuration of both magnesium and aluminium. And as you can see that aluminium has more protons. It has more protons. And it has the same number of shells. So it has more protons, same number of shells. So there should be more attraction for electrons. For aluminium, there should be more electrons, and aluminium's ionization energy must be higher. But aluminium's ionization energy does not follow the trend. It's lesser compared to magnesium, even though aluminium has more protons. And the reason for that is that if you look at the electron that is being removed, the electron is being removed from a higher energy 3p orbital. If you look at the electron that is being removed from magnesium, then it is being removed from a lower energy, relatively lower energy 3s orbital. So because of the lower energy, this electron is going to be closer to the nucleus, and it's going to be more difficult to remove an electron from the 3s orbital of magnesium. Whereas if you look at the electron that is being removed from aluminium, the electron is further away. It's at a higher energy. It is in a higher energy subshell, and it would be easier to remove this electron because it's further away. It's more shielded. So this is what you're going to write as an explanation for why aluminium has a lower ionization energy compared to magnesium, why it's not following the trend, why it has more protons, but still it's easier to remove an electron from aluminium. So I've written down the answer. So in aluminium, electrons removed from a higher energy 3p subshell, this one, and it is more shielded and it is further away from the nucleus compared to magnesium's electron, which is being removed from, you can write the rest of the statement as well, compared to magnesium, where the electron is removed from a lower energy, relatively lower energy 3s subshell, which is closer to the nucleus and is less shielded. So that would be the answer for pair 1, the explanation why aluminium has a lower first ionization energy. Let's move to pair 2 now, which were, pair 2 were phosphorus and sulfur. And again, you had the same issue. Phosphorus has 15 protons. Sulfur, on the other hand, has 16 protons. Sulfur has more protons, but still, it's removing an electron is easier in sulfur compared to phosphorus. So what is the reason for that? So I've written down the electronic configurations of both phosphorus and sulfur. 16 electrons, they have pretty much the same electronic configuration. The last electron that is being removed would be from a 3p subshell. And I've written down the expanded orbital-wise electronic configuration of the 3p subshell. And over here, the reason why it's easier to remove an electron from sulfur is that if you look at the electronic configuration of sulfur's outer subshell and phosphorus's outer subshell, you would notice that in phosphorus, each orbital has one electron. So there is no repulsion because all electrons are in separate orbitals. They're not mutually repelling each other that much. So it would be difficult to remove an electron. But if you look at sulfur's electronic configuration, you will notice that there are two electrons in the same orbital, which means that there is going to be a lot of repulsion between these two electrons. And because of the repulsion, the extra repulsion, as two electrons are in the same orbital, it would actually become very easy for the electrons to be removed because the other electron would be they would try to expel each other's electrons. So because of the extra repulsion over here, it would become easier to remove an electron. So that is what the explanation is going to be, because even though sulfur has more protons, it has the same number of shells, more protons, there should be more attraction, but instead there's lesser attraction because of the paired electrons in this p orbital. This is the statement that I've written, which is that in sulfur, because electrons are removed from a paired p orbital compared to an unpaired p orbital in phosphorus, we should add that in phosphorus. So due to spin pair repulsion, the two electrons would be repelling each other, which is why it would become easier to remove an electron. So due to spin pair repulsion, sulfur is going to have a lower first ionization energy, and that is going to be your answer. And this is a very typical question, and you should remember why these two, sulfur and the other one was aluminium, why these two elements are not following the trend in first ionization energies across the period.